Hello guys, as we have already gone through the full adder and half adder circuits, now we will be talking another adder circuit. This circuit is called binary parallel adder. My name is Bhupesh Vasu and I am here for digital electronics. I will teach you about the basic terminologies and basic combination circuits which are used in digital electronics. Today we are going to start binary parallel adder. In last class we have already gone through this full adder as well as half adders. Now in this full adder and half adders we already know that we can have this carry. We can get the carry from the previous inputs as well. Now in binary parallel adder, it is also the same kind of adder which we have used like full adders. It will have the carry, but the difference is each number or each bit will have a carry which will be forwarded to another adder. Now if we are talking about a binary parallel adder, it adds two binary numbers in parallel form. When we are talking about the parallel form, then it is like this. Now how we can implement that particular circuit? Whenever we need to implement any combination circuit, what we need to identify is inputs as well as outputs. The first input is C0, A0 and B0. Here A0 is the least significant bit of A and B0 is the least significant bit of B. Whenever we are talking about this thing, it will be actually adding in full adder circuit. Right now we are implementing 4-bit parallel adder using 4 full adders. Now what we will get is S1 from this circuit and C1 from this circuit. S1 and C1 are the two outputs in this form. Now when we get this S1 can be shown over here and the C1 can be forwarded to next full adder circuit. Now again there are 3 inputs available to it. The C1 which is the output, the carry of this full adder circuit, A1 and B1. A1 and B1 are the next bits in this particular type where we need to actually add binary numbers. Again the sum will be shown over here and their carry will be forwarded. It will go through this and there will be 4 carry and 4 sums. But C1, C2, C3 actually are already being added in this particular scenario. So we will get C4, S3, S2, S1 and S0, S1, S2 and S3, and the last one is C4. Or we can say that if we are going to signify this S1, this is S2, this is S3 and this will be your S4. Now suppose we don't want to have this 4 adder circuit, full adder circuits. What we can do is we can use full adders and half adders. As we have already understood that full adders and half adders can be used in different terminologies. So what we can use is n minus, if we have the 4, like if you have 4-bit parallel adder, we can use 4 full adders, or we can use 3 full adders and 1 half adder. Again we can use n minus 1, that is 3 into 2 full half adders and 1 OR gate. This is actually full adder circuit and 1 half adder. Again we can go for 2n minus 1, that is 4 into 2, that is 8 minus 1, 7 half adders and 7 OR gates in this 3 OR gates in this circuit to use 4-bit parallel adder circuit. Now how we are going to implement a particular method, how we are going to use a particular method where two binary numbers are actually added. Now suppose we have this A and B. A is 1 0 1 1. When 1 0 1 1 is, that is A, the first number, that is called again, and this is called added. Now this number is 0 0 1 1. Now we will start from this one, from LSB. This is A0, this is A1, this is A2, and this is A3. Again, this is B0, B1, B2, and B3. Now, when we have these two numbers, and there are 4 bits included in this number. Now, the initial carry, when we are talking about initial carry, the first carry is 0, which you are providing over here. Now, first carry is 0. AI, the first bit is 1, as we can see. BI, first second bit is 1. 1 plus 1 is 0. So sum will comes as 0, and there will be carry, that is 1. Now C out is 1. What is that C out? Due to this one. Now this will carry forward to next one. In the next operation, it can be shown over here. 1. Again, when we are adding two numbers, then again 1 plus 1. But there is a carry, so 1 plus 1. The sum will come as 1. 0 plus 1, 1. And there is a carry, which is already there. The same method will follow like this. Now this is how a 4-bit parallel adder has been used. Now why we use this terminology, and there is a different circuit that can be used. Now the carry propagation and the delay in that carry propagation. The first problem we are getting in this particular parallel adder is carry propagation. Whenever the carry has been propagated, there is a slight delay. Whenever the carry is actually propagated in this particular circuit, there is always a delay in the circuit itself, and that delay is actually creating a problem. So the propagation delay in an adder is the time it takes the carry to propagate through the full adder. So it will take some time. There is a time delay, and carry propagation for each propagation delay is the time between the application of the carry in and the occurrence of the carry out. In parallel adder, this propagation delay is presented from input carry to output carry, so it is called ripple carry adder. This is also called ripple carry adder. Now, whenever we have this problem that ripple carry adder, why it is called ripple carry adder? Because there is always a propagation delay from one full adder to next full adder. So this propagation delay will actually create a problem, and this problem can be rectified using another methodology. Now, whenever with this problem that is coming, so we can we calculate that particular delay? Yes, we can do it. Like if we have an n-bit parallel adder and minimum delay to provide the final result equal to 2n TPD. Here n is the bit number of bits which are used, and TPD is the propagation delay in that particular adder. Now each gate will have a propagation delay, so it ultimately what is the result of this particular problem is it will slow down the whole process. If it is slow down the whole process, what we can do is we can use a new type of adder that can be used, and it is called look ahead carry adder. This will actually provide the solution to this problem, because each time there is a propagation delay from one adder to another adder, and each time a carry has this propagation delay, the output will have some kind of delay. And ultimately, if number of full adders has been used in that particular circuit are quite large enough, that propagation delay can create a problem. As we have already understood that propagation delay is 2n TPD, so this will create a problem for all of us. Now, let's talk an example. Like if, for example, is like one bit full adder takes 75 nanoseconds. This is the example of how this is creating problem. Like in a circuit, a 1 bit full adder takes 75 nanoseconds to produce sum, and 50 nanoseconds to it takes 75 nanoseconds to produce sum and 50 nanoseconds to produce carry. Now a 4-bit parallel adder is designed using this kind of full adder. The maximum rate of additions per second can be provided by 4-bit parallel adder is A into 10 to the power 6 additions per second. Then what will be the value of A? Now it is asking, now one full adder is taking 75 nanoseconds to produce a sum and 50 nanoseconds to produce a carry. Now it is a 4-bit parallel adder, and so there are 4 full adders are provided, and each adder will take this much time to produce sum as well as carry. Now A into 10 to the power 6 are additions per seconds which this particular adder can be propagate or can be shown. Now what is the value of this? So minimum propagation delay is what? 3 into 50 into 75. Now if you are calculating this thing, 50 plus 75. Now 50 plus 75 is roughly, if you are talking about this one, is 125 into 3, and that will come as 225 nanoseconds. Sorry, I made a mistake. 3 into 50 plus 75, because 50 is the time propagation delay to produce that carry. So 3 into 50, 3 parallel adders are there, 3 full adders are there. 3 into 50 plus 75, that is to produce sum. Now sum has been provided. 225 nanoseconds will be there. So maximum addition per seconds are 1 divided by 225 nanoseconds, and that will come as 4.44 into 10 to the power 6 additions per second. So value of A is 4.44. What it signifies is 4.44 additions, 4.44 and 10 to the power 6 additions per second can be done using this formula. But there is a propagation delay, and that is 225 nanoseconds. Literally 225 nanoseconds is the delay which has been creating a problem. So if you are talking about a big circuit, this can create a problem. Thank you guys. Now, in the last topic, we have already discussed about parallel adder, and there is a propagation delay circuit. Every propagation delay is creating the carry delay as well as the sum delay. Now that particular carry delay will actually affect the overall outcome of this particular circuit. Now, what we need to do is we use look ahead carrier. In this, what is the use of this? It speeds up the process by eliminating ripple carry delay. Now, whenever there is a delay out there, it just cancel out. Now, what it do is examines all input bits simultaneously and generates carry for further stages. Every time a particular bit is added, every time 2 bits are added, it just processes simultaneously. At the same time, it generates carry for further stages. As we have already seen in the last slides and last parallel adder circuit, every time a particular carry is generated, it always propagated and added into next stages of that full adder. Now, how this particular problem has been eliminated? Now there are 2 things out there. In every full adder circuit, the first is PI, that is every time 1 bit is added to the other bit, the sum of that bit is AI XOR PI. That is the normal thing which we have been doing, and the output of this is the sum, and then their carry has been propagated. Then there is GI, that is AIBI. This is the carry which has been generated, and this carry will be generated at each stage of that full adder. Now, let's talk about this particular look ahead carry adder circuit. Now in this look ahead carry adder circuit, we use two half adders. A and B are the two numbers, digital actual number, which needs to be added. Now A and B are actually going through this process, and now this is the XOR gate. This generate the PI, which we have already explained over here. In this, a carry will be propagated to the next stage of next full adder. These two are two half adders in this particular circuit. Now this is also generating a carry, which is AIBI. AIBI is this thing, AND gate is there, and this GI is actually moved forwards. What we will do is PI will be added towards this one. This PI and this CI, initial carry, will actually generate the sum. PI XOR CI. This will generate the sum because these two half adders will actually make a one full adder circuit. So PI XOR CI will generate the sum of that particular stage. Now this GI will be ANDed over there, and PI will be there. Now PI and GI are already there. Now what we need to do is that CI and PI needs to be ANDed together, and that output needs to be XORed, and this not XORed, this is the OR gate, logical OR gate, and this output is going toward this one, and this will generate the carry for the next stage simultaneously. What we are doing is this. If we are talking about SI, that is like the sum of first stage, that is P1 plus C1 or PI plus CI. Now the carry which propagates to the next stage is always like this, GI plus PI CI. It is already there. Now if you are talking about the first carry is the C0, that is the input provided to the first full adder circuit, that is C0. Afterwards the carry which generates will be actually propagates to the next adder, and this is C1, that is G0 plus P0 C0. Now again C2 it will be generated in next stage. We are talking about right now, what we are talking about is the full adder circuit. 3 full adder circuits, 4-bit full adder circuit, 4-bit parallel adder circuit. Now C2 will be there, that is G1 plus P1 C1. Same C3 will be G2 plus P2 C2. Now every time when we are going through these equations, now when we are talking about the C1, G0 plus P0 C0. Now putting this value in this particular equation, what you will get is G1 plus, now P1 is there, G0 P1 G0 plus P1 G0 C0. That will be there. So when you put this equation into this equation, so C3 will become as P2 P1 P0 C0 plus P2 P1 G0 plus P2 G2 plus G2. That will be the final carry which will be generated, C3, and that will be propagated. Now this process is actually done simultaneously, and this process actually eliminates all the delays in that particular parallel adder circuit. Now the next topic which will come in our mind is, now what is the meaning of all this? What is the meaning of this? Now as we know that Boolean function for each output carry can be expressed in sum of products form, and this each function can be implemented with one level of AND gate followed by OR gate. Now it can be simplified, it can be shown like this. Now number of methods are available to that, so we can do it. I will show it to the slides itself that how it can be generated. Now for example, what we need to remember is, in a look ahead carry scheme, if we are talking about the n bit addition requires n plus 1 OR gates, or n it requires n plus 1 OR gates, or n plus 1 by 2 AND gates. Now to generate a carry output, the carry circuit requires 3 logic gate delay, and for some output it requires 4 logic gate carry delays. Now if you are talking about a parallel bit adder, there will be a serial adder too. Now if you are talking about the serial adder, this serial adder circuit is quite different from the parallel adder circuit. Now in parallel adder circuit, each time what we are doing is we just adding two bits parallel, as we have seen in the last example. When we are talking about a particular problem, if we have a problem and if we need to add two numbers, and two numbers which will be shown in digital form, not like every number, every bit from LSB to MSB will be added, and they will be added parallel. In serial bit adder, this process is quite different. Now what we need to do is, in serial adder, in the serial adder circuit, what we are going to do is, it is used to add two binary numbers, and these two numbers will be added in serial form. What is the meaning of serial form? When the two binary numbers to be added serially, they store two shift registers designated as A and B, and the circuit adds one pair at a time. Every time a shift register has been used, and it will be added one number at a time. So one pair at a time with the help of one full adder circuit. Now what will be the diagram of that thing? Like, if you are talking about serial adder, what we need to do is, we need to use two shift registers. Two shift registers, suppose it is designated as A, and other shift register that will be shown as B. Now two shift registers have been used, and shift control is there. One clock has been provided to it. Now this is called augment. Again, this here is augment. Now these output of these two shift registers are added in full adder circuit. This is X, this is Y, and what we need to do is, we use D flip-flop. Now why we are using this D flip-flop, and why we need to put this is called SI, this is called SO, SI, and serial input and serial output. Now we can see in this circuit we use two shift registers, one full adder circuit and one D flip-flop. This is the D flip-flop which has been used. We have already discussed the functions and functionality of D flip-flop. There is, what we can see is, there is serial input which has been provided over there, and there is a shift control over there. This shift control is provided to both the shift registers, shift register A as well as shift register B, and this serial input will be provided as the third input. In this, the serial input has been provided through this full adder circuit, where it has been generating a sum bit. Now sum bit will be provided again as a serial input, and the output of this shift register is SO. Again the output of shift register is SO, and the output of D flip-flop will be provided here. So 3 bits will be there, the Q bit, X and Y. 3 bits will be added in this full adder circuit. Now how it is different? Now every time whenever we are talking about shift registers, whenever we are talking about parallel circuits, there is a difference between parallel adders and serial adder. Now in serial adder, what is the difference is, the first is the serial adder uses shift registers, whereas in parallel adder it uses registers with parallel loads. The second thing is, serial adder requires only one full adder and one flip-flop, where in that particular parallel circuit, the number of full adders requires are equal to the number of bits in every number. So whenever, if we need to add 4 bits, then we need at least 4 full adder circuit. But here we use only one full adder and one D flip-flop and two shift registers. Every time we do that, this particular circuit will actually give us the output. The last one is what we are getting is in serial adder is a sequential circuit. As we can see, that clock is provided. As we can see, that output has been again propagated and get back to the particular input. It has been used as the input. So this is one of the significant example of sequential circuit. Whenever we are talking about sequential circuit, the output has been provided as an input. So there is a particular thing like whenever we were discussing earlier, that the difference between combination circuit and sequential circuit is quite significant. And what is that? That its output will depends in the combination circuit. Output will depends on the present state only, but in sequential circuit the output depends on the previous stages as well and the next stage as well. So the output will vary. So shift register serial adder was one of the best example of sequential circuit. And the last example of that parallel adder is it is just the combination circuit where we use parallel loops. Now, one of the other adder which has been used quite frequently in digital electronics is BCD adder. As we know, the BCD or binary coded decimal is the number where each number has been changed. And BCD has been used quite frequently in all the input-output devices. So what we need to do is we need to understand there is a difference between the normal adder, that is parallel serial adder, and the BCD adder. It works like the same, but it comes in different category. Now in BCD adder circuit, if you are talking about the BCD adder, if we need to add two 4-bit BCD, then what we need to do is we need to add them simultaneously, and the particular adder circuit is quite different from the circuit which we have been using. Like if you are using a particular circuit like 4-bit binary adder circuit is there, and there is another 4-bit binary adder circuit is there. Now what we need to do is we need to put the carry in, C in or there, and all the bits, as we all know that there are 4 bits, so AND bit as well as addend bit are provided over there, and the output, the carry output, C out, and that is shown as K, and the output of this one, that is Z8, Z4, Z2, Z1 is provided over there, and S8, S4, S2 and S1 is provided over there. What we need to do is we need to put them as inputs over there. Like this, AND bit and addend bit. These are Z2, Z8, Z4, Z2, Z1, and then what we need to do is we take 2 and ANDed them. Again, the first bit Z8 and Z4 has been added, and then is another AND gate which has been used quite frequently, and what we need to do is to use the third bit, and these bits has been logic OR gate, and there will be carry out, and this will gives us output carry, and this output carry has been provided over there As we know, it is a 4 bit. 4 bit came from this one, 4 bit came from this one, and this will be the final output. This will be the output carry, and this will be the output of that sum and the BCD adder circuit. Now what we have two BCD numbers, and we know that BCD numbers are quite different. So what we need to do is we need to understand them differently. It will be actually discussed